In this section is going to be a summary of curve sketching. So these are the 8 areas we're going to gather information to help us sketch our graph by hand as accurately as possible. And then at the very end, I'm also going to talk about how to find the equations of a slant asymptote. So the guidelines here, and I will always point this out, what you have to find. So it's important to know the domain of a function, the intercepts, x and y intercepts. We're going to test for symmetry, whether a function is even or odd, so that goes back to chapter 1. We're going to find the horizontal and the vertical asymptotes, and like I said at the very end, we'll talk about slant asymptotes. We want to find intervals where a function is increasing and decreasing. We want to find the relative extrema, the intervals where our graph is concave up, concave down, and if there's any points of inflection, we want to find them, and then ultimately we want to sketch our curve. All right, so here's our function, and this is the same example I'm going to do in class Tuesday, only because if I don't finish this before Tuesday's group has to take the differentiation exam, they could still finish looking at the same example. All right, so first we're going to go ahead and find the domain. And in this case, because we have a rational expression, the domain comes from the denominator. So I'm just going to really say x squared minus 1 cannot equal to 0. And then I'm going to go ahead and just set it equal to 0 and solve for x here. So x squared would equal 1. Take the square root. X is going to equal plus or minus 1. So now our domain, I'm going to write this in interval notation, is going to go from negative infinity, pretty much all real numbers except these two. So I'm going to stop it at -1, pick back up, -1 to 1, and then from 1 to infinity. Now B for the intercepts, I'm going to find both the x and y. So to find the x-intercept, I simply set y equal to 0. To find the y-intercept, I set x equal to 0. So if I set y equal to 0, that's going to become 0 is going to equal 2x squared over x squared minus 1. Now I could just multiply both sides by x squared minus 1. Or whenever I have a fraction, the only thing that's going to cause it to be 0 is if the numerator is 0. So I'm still going to get a 0 on the left side because 0 times anything is 0. Over here, the x squared minus 1's divide out, and I'm left with 2x squared. Divide by 2, take the square root, so x equals 0. So I have an x-intercept of 0. Find the y-intercept, set all the x's equal to 0. So I'm going to get 2 times 0 squared over 0 squared minus 1. I'm going to get a 0 over a -1, which is 0. So I have a y-intercept of 0, which pretty much means the point 0, 0 is going to be on the curve. So looking at an x-intercept of 0, y-intercept of 0, which means it's the origin. All right, for C, when we test for symmetry, this is to determine if our function is even, odd, or neither. So remember, to test to see if our function is even, f of the opposite of x needs to turn back out to equal f of x, and that means our function would be even, and it has symmetry with respect to the y-axis. If we substituted in or evaluated f of the opposite of x and we got the opposite of f of x, that means our function's an odd function and it's symmetric with respect to the origin. So I just rewrote our function right here. So let's go ahead and test. We'll have f of the opposite of x is going to equal 2 times the opposite of x squared over the opposite of x squared minus 1. Now if you notice, both of these exponents are even, and even for the 1, that's really an x to the 0 afterwards. So if I square a negative x, that's still going to be x squared. Just think, because if I have a -1 here, squaring a -1 turns into a positive. And then I have it over, again, another positive x squared minus 1. We have to state this. Now this is equal to f of x. So since f of opposite of x is equal to f of x is an even function, and it is symmetric with respect to the y-axis. And that's going to help us when we go to sketch our graph by hand. All right, next we're going to find horizontal and vertical asymptotes. Now vertical asymptotes, just like our domain, is going to come from our denominator. So if I set x squared minus 1 equal to 0, just as I solved for part D, or part A, I'm just going to say C part A for the work. So we add 1, take the square root, so x equals plus or minus 1. So we have vertical asymptotes at x equals -1 and x equals a positive 1. Now for the horizontal asymptote, we need the limits at infinity. Now since this is a very simple rational expression, there's no square roots, there's no absolute value, I really don't need to take the separate plus or net minus infinity here, so I could keep them together because the same thing's going to happen regardless of the sign. So I'm just going to write as x is approaching plus or minus infinity of 2x squared over x squared minus 1. So this is where I want to divide everything by the largest power of x in the denominator. So I'm going to divide everything by x squared. So I'm going to have 2x squared over x squared, and then x squared over x squared minus 1 over x squared. I want to simplify this. I can't just cross things out now. I need to show I get a constant over a power of x. So up here I'm just going to get a 2 over a 1 minus 1 over x squared. So the only constant over power of x I have is right here. Now as x keeps increasing or decreasing without bound, this is going to go to 0, and I'm left with the limit of a constant, so I get 2. Therefore I have a horizontal asymptote of y equals 2. So those are both going to help us. Those are actually going to be the first things we graph when we go to make our sketch. All right, now for part E, we want to find the intervals where a function is increasing and decreasing. So this means what, guys? We want to find the first derivative. So pause the video, go ahead and find f prime of x, and we'll see what you get. All right, so here we have to use the quotient rule. So f prime of x is going to be low d high will give us a 4x, minus high d low will give us a 2x. And then this is all over x squared minus 1 squared. Now we want to simplify that numerator in order to be able to ask ourselves 2 questions to find our critical numbers. So this is going to become a 4x cubed minus 4x, and then minus a 4x cubed here, all over x squared minus 1 squared. So now if you notice, the 4x cubes cancel, and we're left with a negative 4x over x squared minus 1 squared. So that is our first derivative. So now we're going to ask ourselves 2 questions. Is f prime of x ever equal to 0? Is f prime of x ever undefined? So f prime of x is only equal to 0 when our numerator is equal to 0, which happens at x equals 0. Is our first derivative ever undefined? This happens when our denominator is equal to 0. So because it's squared, I could still just take what's inside and set that equal to 0. Now we already solved this twice. This is going to give us a plus or minus 1. However, I'm going to point out we know our function does not exist. We have vertical asymptotes at x equals plus or minus 1. So we'll see what to do with that here in a moment. Next, we want to justify, which means we need to draw our number line for f prime of x, put our critical numbers on it. So right now 0, -1, and 1 are still critical numbers. So I'm going to put a -1, a 0, and a 1. And I want to test some values, and I'm going to test them into this part right here. All right, so let's say I pick a -2, let's say I pick a -1/2, +1/2, and then a 2. Now, my denominator, because it's a quantity squared, no matter what's in there, I square it, it's always going to be positive. So I really just have to pay attention to the numerator. So if I took a -2 times -4, that's positive. A positive over a positive is positive. Likewise, for a -1/2, -1/2 times -4 is positive. Positive over a positive is still positive. If I substitute it in a 1/2, 1/2 times -4 is negative. Negative over a positive now is negative. Same thing with 2. 2 times -4 is a -8. Divided by a positive will still be a negative. So this tells me f of x is increasing from -infinity to -1, also increasing from -1 to 0, decreasing from 0 to 1, and then decreasing from 1 to infinity. So the way I'm going to write this, our function is increasing. Now, because we have asymptotes at x equals -1 and 1, I cannot connect these intervals here. So it's going to be from negative infinity to negative 1, and then from negative 1 to 0, decreasing from 0 to 1, and then from 1 to infinity. All right, so that answers part E. For part F, we want to find the relative extrema. So I'm just going to answer this here. Actually, I'm going to go to the next page because I already have it written out there. All right, so I'm just looking at this again. Now, notice f of x is going from increasing to increasing, plus we have a vertical asymptote here. So we're not going to have any maxes or mins at the vertical asymptotes. And also, if you notice, we're not changing from increasing to decreasing at x equals negative 1 or 1. Just right here, we are going from increasing to decreasing. So perhaps it looks like this, but regardless, we have a relative max at x equals 0. So I want to find f of 0. And I kind of already did this. Remember, it's 2x squared, so this becomes 2 times 0 squared over x squared minus 1. So this gives us a 0. So the way we're going to write this, the relative max, we're really looking at the point 0, 0, so the origin, but we want to write it this way. The relative max is y equals 0 when x equals 0. So there's our answer for part F. Yes, you have to write it that way. All right, next we're going to check for concavity. So I just have the first derivative rewritten again. Pause the video, go ahead and find the second derivative, but do this very carefully. Okay, hopefully you were able to complete that. If not, still pause the video and continue to work. So f double prime of x, we have low, which is x squared minus 1. D high becomes a negative 4. Minus high, so a negative 4x. D low, we have to use the chain rule, so it becomes 2 times x squared minus 1 to the first, times the derivative of the inside stuff, which is just a 2x. And this is all over x squared minus 1. Now, if we squared something that's squared, we multiply the exponent, so we could just say it's a 4. Now, before I do any kind of factoring, and I want to do that, I'm actually going to go ahead and clean this up a little more. I'm going to put the negative 4 first. X squared minus 1, I forgot the square there. Now here a negative 1 times or minus the negative 4x is going to become a positive 4x. So I could go ahead and multiply that together, then multiply it by 2, then multiply it by 2x. Those are all monomials. So I'm going to get a positive 4x times 2 is a positive 8x, times another 2x is going to give me a positive 16x squared, times x squared minus 1. All over x squared minus 1 to the 4th. Now, if you notice, without actually factoring, I notice that I've got a binomial here of x squared minus 1. I have got it that squared. Over here, I just have one factor of x squared minus 1. And then down here, I've got 4 of them. So what I could do is just divide every term by that binomial x squared minus 1. So now this gives me a negative 4 times x squared minus 1 to the first plus 16x squared. I'm dividing this out. And then it's all over x squared minus 1 cubed. Now I can distribute the negative 4. So I'm going to get a negative 4x squared plus 4 plus 16x squared all over x squared minus 1 squared. Combining like terms, I'm going to get a 12x squared plus 4 over x squared minus 1. Actually, that's to the third power right there. X squared minus 1 cubed. All right, so again, we want to justify. Actually, before we do that, we want to ask our two questions before we justify. So I want to know, where is f double prime of x equal to 0? Where is f double prime of x undefined? So what I'm going to do is set my numerator, again, equal to 0. I'm going to subtract 4. divide by 12. So x squared is going to give me negative 4/12, will give me a negative 1/3. But if you notice here, if I'm squaring it, I have to take the square root. I can't take the square root of a negative number, so that's never true. So I have no x values that would cause the numerator to be 0. In fact, it's never going to be negative. It's always positive, because no matter what I square is positive, multiply that by 12, that's still positive. Add 4, that's still positive. So in this case, the numerator is always positive. Now, where is my f double prime of x undefined? And we're back to the x squared minus 1 equals 0. So we know that's x equals plus or minus 1. Now we're going to justify. We have our critical numbers. But if you remember, we also have asymptotes at those x values. So I have my number line here, but now this is representing my second derivative. So notice when we did part E, I labeled this f prime of x. Now I must label this f double prime of x. So I have my negative 1, I have my positive 1. We still need to do this to show where our graph is concave up and concave down. So let's choose a negative 2, let's choose a 0, let's choose a positive 2. I'm going to substitute it into this expression where I know my numerator is always positive. So if I substituted a negative 2 into my denominator, negative 2 squared is 4, 4 minus 1 is positive, so I get a positive over a positive. I'm going to get a positive here. If I substitute it in a 0, that's still just going to give me a positive 4. 0 squared minus 1 is negative, and a negative cubed is still negative. So I'm going to get a negative where x is equal to 0. Now remember, our function is even, so I should expect to get a positive over here as well. Again, I'm going to get an always positive. 2 squared minus 1 is still positive. So this tells me f of x is concave up in this interval, concave down, and then concave up again. So we'll say concave up from negative infinity to negative 1, and then from 1 to infinity. Concave down from negative 1 to 1. Point of inflection would happen when our concavity changes, but in this case, f of negative 1 does not exist. F of 1 also does not exist. So we have no points there, so no points of inflection. Looked like we were going to, but because of this fact, this happened. All right, so that was part G. Now we're going to make a sketch of the curve. So if you just take a look at how I numbered here, just to get a good idea, I just counted every 4 squares on my x-axis were 1, and then I counted by 2 here. So pause the video and make a sketch of this. All right, and we're going to go ahead and draw in our horizontal and vertical asymptotes first. All right, so if you remember, because I said this plenty of times, we have a vertical asymptote at x equals negative 1 and x equals a positive 1. We have a horizontal asymptote at y equals 2. So that's very important. Now we know our domain matches this because it's negative infinity to negative 1, and then everywhere in between negative 1 to 1 and 1 to infinity. We also had an x-intercept and a y-intercept right at the origin. That was also our max value. So now if we go back and look from negative infinity to negative 1, and you have to look at what you just wrote out. It's going to be too much for me to keep going back and forth to the pages. But from negative infinity to negative 1, our graph was increasing, and it was also concave up. So this is what an increasing and concave up and staying within the asymptotes here. This is what our graph looks like in the upper left corner. Now from negative 1 to 0, our graph was increasing, and then if you look at the second derivative, we were concave up. I'm sorry, concave down. So if we're increasing and concave down, it's like we're starting very close to this asymptote, and we start to look like this as we go to our max. Now, what could be helpful here is knowing that this is symmetric with respect to the y-axis. I could fill this in over here, and then we could verify it with our number lines. When we're between 0 and 1, we should be decreasing and still concave down. And then up here, again, if we're symmetric, we know that this last piece should look like this, just as if we folded over this part right here. But the last part, we should be decreasing and concave up from 1 to infinity. So this is what the graph of y equals 2x squared over x squared minus 1 should look like. But we used all algebra and calculus to help us find the important pieces here. All right, so our last few examples are going to focus on slant asymptotes. So here's some information. A slant asymptote is going to occur when the limit of a function as x increases or decreases without bound equals infinity. And this happens when the degree of the numerator is 1 more than the degree of our denominator. Because when we divide, if we're just 1 degree off, it's going to give us a long division here. It's going to give us like a y equals an mx plus b. So we only want a degree of 1, which is going to give us a line. And we call that a slant asymptote. The equation of the slant asymptote is found by long division. The slant asymptote means the vertical distance between y equals f of x and y equals mx plus b approaches 0, so they get closer and closer as x increases without bound, or just looking at it in terms of a limit. So pause this video now so you can finish writing this down, and then we're going to take a look at a couple examples. All right, so all we're going to focus on here is finding the equation of the slant asymptote. Now, if we were to find the limit here, going through the process of dividing everything by the largest degree of 2, we would get an infinity. But we can avoid that. We're going to do some long division here. So I'm going to start with x cubed. Notice the degree of my numerator is 1 larger than the degree of my denominator. So I'm going to put the x squared plus 1. So if you took college algebra or pre-calc, you should have gone over long division, polynomial long division, or synthetic division. If not, just follow along here. Now, when we do long division, this is like saying something to the third power is like looking at a number that's in the thousands. I need to fill in the other place values. So I'm going to put a plus 0x squared plus a 0x and then a constant, so plus a 0. So now I need to take x squared into x cubed. So x squared times what is x cubed? Just an x. So because this is where my 0x is, I'm going to put an x up here. And just like long division with numbers, I'm going to multiply x times x squared is x cubed. I don't get an x squared here, so I'm going to still put 0x squared. X times 1 is x. But now I go through and I subtract everything. And when I do that, x cubes are gone. I don't have any x squares. 0x minus a 1x is still just going to give me a minus a 1x. And then normally, if this were any other number, we would bring it down, but we don't have to. So now x squared can't go into a negative x because it's a smaller degree. So what I do is I write this as a remainder. And I'm going to put some minus an x back over what I'm dividing by. So now as x increases without bound, a negative x over x squared plus 1, if I still do the limit here and divide everything by x squared, I'm going to get a negative x over x squared, and then x squared over x squared plus 1 over x squared. So this is going to become a negative 1 over x, and then 1 plus 1 over x squared. So now this will go to 0. This will go to 0 as x increases without bound. And I'm getting a really small number over a 1 here. So as this keeps getting smaller and smaller, this is practically going to go to 0. So I could just ignore this part. And this is what I'm left with. So the slant asymptote is y equals x. Now I'm in the process of renewing my computer software to show you the Inspire. But if you want to do this on Desmos or on your own graphing calculator, go ahead and graph this function, f of x is equal to x cubed over x squared plus 1, and then graph the line y equals x. What you should see is that this line, y equals x, kind of splitting, going right between the graph, and as you keep increasing x, the graph is going to approach this line, y equals x. So let's go ahead and try another one. This is our last example. So we're going to find the equation of the slant asymptote. So we have y equals 1 plus 5x minus 2x squared over x minus 2. So I'm going to rewrite it this way. Negative 2x squared plus 5x plus 1. I have an x squared, I have an x to the first, I have an x to the 0, so I don't need any place fillers. I'm going to put an x minus 2 on the outside. X goes into x squared, or x times what is a negative 2x squared? It's a negative 2x. So this is my 5x term. I'm going to put a negative 2x right here. So negative 2x times x is a negative 2x squared. Negative 2x times a negative 2 is a positive 4x. But now what I want to do is subtract. So if I subtract a negative, that's going to turn it to a positive, and then I'm going to subtract this here. So negative 2x squared plus 2x squared is gone. 5x minus 4x is x, and then I bring down my plus 1. So now x times what is x? A positive 1. 1 times x is x. 1 times a negative 2 is a negative 2. But I want to subtract these, so this becomes a minus, this becomes a plus. These are gone, so I get a 3. So that's my remainder, so I'm going to put a plus 3 over x minus 2. Well, what's going to happen as x keeps increasing without bound? This remainder is just going to go to 0. So the equation of my slant asymptote is this right here. Y equals negative 2x plus 1. And again, you can check, graph this function, graph the line, y equals 2x plus 1. That should show a nice slant asymptote that the graph is sort of approaching as x increases without bound. All right, so that's the lesson on section 3.5. On Thursday, I'm going to go over some optimization problems, section 3.7. Take care, guys, and let me know if you have any questions.